All right, and we are live and on the air. So this video is going to be based on calculus, and in this video we're going to try and find a little bit of inspiration as to why to study calculus. Calculus, after all, is a very useful field. It's used everywhere. So I'm just going to give it a few minutes and see if people decide to show up. I'll probably give it about 5-10 minutes, and if people don't show up, that's fine. I'll continue anyway. If they do, great. I would rather people show up so that way I can comment or address concerns people have or common questions and things like that. If they do, it could be I need to share this, so let me do that. Move the word around and see what happens. This is fun. Live streaming, first time ever. I've been on streams before, but never actually hosted one. It's a brand new world. It could be I need to share this, so let me do that. Do. Oh, people. Okay. All right. Midnight Sparkle says f of x equals 3x squared. So, good to see you, Midnight. Welcome to the stream. So, without further ado, now that people are watching, well, I don't know. Maybe we'll see if more people decide to join. All right. Looks like there's one viewer, but that's fine. One viewer is better than no viewers, after all. All right. Let's see if I can screen share. I can screen share. So screen sharing, present to everybody. And let me see if it is showing the little PowerPoint I brought up. Let's see if it's showing. Folks in the live chat, is the PowerPoint showing? Do you see a PowerPoint? If so, that is great. If not, that's also great because it's a learning experience. it's a learning experience. All right, great. So now we can deal with the question of why calculus? So, why calculus? Well, calculus is just a very useful system of mathematics. It has a wide it has a wide range of applications. We use it generally to make our lives easier, and also because it helps in modeling very odd and sometimes common mathematical behavior that we observe. How is this field relevant? The better question would be, how is it not? The field of calculus is used in basically every science. I can't think of a science where it isn't used. And the main reason for that is the universe we live in is always changing, and there has to be some way we can express these things. So, before we dive into everything, let's think about calculus and its origins. So, the founders of calculus, or the founder of calculus, there are two of them, oddly enough. The first of which is Newton, and the second of which is Leibniz. And they both developed calculus independently. Newton, when he developed calculus, went on to develop modern physics, or rather, build the foundation for modern physics. And Leibniz was what we would probably call nowadays a pure mathematician. And he created the field of calculus independently of Newton, and he used a little bit different notation than Newton did. And that turned out to be useful in some cases. We don't need to get into notation now. We'll have plenty of that when we get into integrals and other topics. So change, the language of the universe. That's very true. So calculus itself is the study of change. And the universe is constantly changing. We are always faced with situations that are, for lack of a better expression, non-static. They are typically interacting with other things, so it's an open system in that sense. We observe change on a day-to-day basis, and in mathematics, we seek to express this change. Yes, this generally is the role of functions. They are arbitrary in their role, but usually, when we use them, they're trying to describe a physical behavior. And we tend to note, when we observe something, that things that we observe often depend on more than one thing that are consistently changing. Well, that's true. The particles in air, for instance, are constantly changing. They're constantly interacting with each other. The velocity they have, the momentum they have, is constantly going back and forth, always in flux. An application of calculus is a field of mathematics that is called differential equations. Differential equations is very similar to calculus. It uses it quite heavily. And it is an interesting field in the sense that we can describe a lot of physical phenomena. And differential equations, just like calculus, has many applications. So, an example of a differential equation. Before we do that, we actually do not need now to focus on why the solution to a differential equation that I presented is valid. For now, you can verify the solution's validity on your own. If I am successful with these videos, then I will show you how to solve differential equations, and that will be its own thing. So, in differential equations, commonly in differential equations, commonly we like to use what's called prime notation. The prime that I'm talking about, for instance, if you see the y double prime, what looks like the two apostrophe marks, the prime in this case doesn't indicate a new kind of function. even though it kind of does, that's kind of a half lie. The prime indicates the order of the derivative. What do I mean? Well, if I say y prime, then y prime means the first derivative with respect to some variable of y, and the prime denotes that being the first derivative. Y double prime, on the other hand, is the second derivative, or the first derivative of the first derivative, or rather, the derivative of the first derivative. And an example of two differential equations that I've listed are the second derivative of y plus a times y is equal to 0, and the constant a has an arbitrary value. It does not matter what we designate it to be. And the solution of this differential equation is given by c1 times the cosine of t square roots of a plus c2 sine t square roots of a. And notice, in this case, we will discuss this later, the c1 and c2. We noted earlier that a is a constant value. It does not change. C1 and C2 are very similar. C1 and C2 are arbitrary constants. They can have any value they want to. They can be real, they can be imaginary, they can be 0 if they want to. However, we'd rather than not. C1 and C2 are used for the reason that when, as we'll find later, when we differentiate a function, for instance, if I differentiate x plus 3 with respect to x, that turns out to be 1. But the issue, though, is the derivative of any constant that is taken is 0. And that makes sense intuitively. That doesn't even need to be mathematically really thought of. That's a logical conclusion. If something is constant, then the rate of change, instantaneous rate of change rather, which is what the derivative is, will be 0, because a constant is constant. It's not changing. And C1 and C2 are signifying that any specific set of constants, or any arbitrary constants for that matter, are solutions, along with the cosine and sine functions, of the differential equation. What's interesting is in differential equations, you will run into what's called initial value problems that, in essence, tells you how the function behaves. And this actually gives you specific values for C1 and C2. Just trying to solve a differential equation will not tell you about what C1 and C2 are. They're arbitrary. The same thing holds for the second differential equation. Y double prime minus b times y is 0. And the solution is c1 e to the negative t square root of b plus c2 e t square root of b. That differential equation is solved in a different manner, but it's similar. The useful thing is that c1 and c2, like before, are constants. And since this is not a course on differential equations, we don't need to consider how exactly these solutions are obtained. If you would like to, though, you may attempt to solve them, or if you would also like to, you may verify that these are solutions of the differential equation. A fun aspect of differential equations is that, as I noted earlier, the prime notation has a very interesting property to it. So the second derivative of a function plus an arbitrary constant times the first derivative is said to be 0. And it turns out, in general, that for an nth order differential equation, I will have n arbitrary coefficients along with n functions, which is quite interesting. For now, the purpose of these videos is to consider functions that are dependent on one variable only. This is done for the sake of simplicity and also because multivariable calculus is its own field. The field of multivariable calculus is used heavily, but it has its own restrictions to it. It has its own set of rules that we have to consider. We will examine functions that are quote unquote real. So you may ask, what is it that I mean by a real function? Well, real in this case does not mean real as in something we find in reality. Mathematics by its nature is abstract. Real actually refers to a kind of number. So in pre-calculus, you learn that there are primarily, among the other kinds of numbers that you encounter, two general classes of numbers: real numbers and complex numbers. Real numbers are, pi, e, 3, 4, 1, 2, 0, -1, -2, all those fun ones. And they have no what's sometimes referred to as an imaginary component. Complex numbers, or sometimes called imaginary numbers, are complex valued, which means that they have an imaginary part. In pre-calculus, we call the imaginary unit I, and this imaginary unit I is actually very special. It has implications for when we graph functions, when we try to find the area of functions. It actually makes it quite difficult for reasons I'll explain briefly. So, calculus develops itself upon one foundation, and it creates itself two topics, or well, two generic topics at least. The first of which is the what we are operating from, what gives us the derivative and the integral operator r is what's called the limit operator. And the limit operator is special in the sense that it produces these two functions specifically. It can produce other functions, but these are the two that we're concerned with. When we discuss derivatives, we will discuss how exactly limits make the concept of derivatives possible, and how exactly integrals are possible, and how they are defined in terms of limits. So what are derivatives used for? And that's a very good question. Well, derivatives on their own are used for they're used to try and describe the behavior of a function. They're used to try and find things about a function we normally would not expect, which is useful. And in addition to that, when we are examining functions, we can take more than one derivative. We can take the first derivative, we can take the second derivative, a third derivative, so on and so forth. And in particular, a very special derivative called the second derivative, which is the derivative of the first derivative, under the assumption that a function, in terms of time, belongs to a set of functions c squared. This simply means that f of t belongs to a family of functions that is twice differentiable, at least. C squared actually means that it is twice-wise differentiable. If I put c to the infinity, this would mean that the function is infinitely differentiable. This is a notation that is commonly used and that in advanced mathematics you use in order to qualify things with theorems. Yes, the derivative of a constant is 0, hence the name constant. So the second derivative, again, tells us that about the maximum and minimum of a function, if it has any, which it usually will, unless you're talking about a straight line, which is a constant, so its derivative will be 0. This has a typo. It's supposed to say inspiration for the derivative. And the idea here is saying, suppose I want to construct a rectangle or a fence. Most fences are rectangles, some are not, but that's fine. And that I want to have it with sides A and B. And I know its area, and I know its perimeter, but I don't know its length. I want to find the lengths that optimize these particular aspects of the fence. And that's actually quite the useful thing to do. For instance, if I have a kid or if I simply want to build a fence to encapsulate something, I may want to figure out, okay, I have this much space, I have this much fence. How do I want to use my area effectively? And later on, we will find ways to solve for A and B. So an inspiration for the integral. So suppose when I throw a ball, and this will never happen, by the way, such that when it falls and it reaches a maximum height, when that ball falls, it achieves half of its maximum height. And it does that every time. So I drop a ball from 1 foot. Once it bounces and it travels back down, its new max height was 1/2, then it's 1/4, then it's 1/8, then it's 1/16. And what I want to do is, as this ball bounces continuously, I want to find out how much space this ball travels. And this is actually a very interesting problem. It requires integration to solve it. And the idea for integrals is that for functions tend to describe phenomena that exist in nature. And unfortunately, in algebra, the only thing we know how to find the area of, or area for, is a straight line. Well, unfortunately, most things that we're trying to describe aren't as simple as that. So the only way we really get off the ground is by finding new functions and finding ways to obtain their derivatives and finding ways to describe their rates of change. The integral, as a matter of fact, is the opposite of the derivative. So where the derivative tells us the rate of change of a function, the integral tells us, or the integral is asking the question, what function, when differentiated, gives the result? When we study integrals in more depth, this will become more obvious. So hopefully this serves as a sufficient introduction for integrals and derivatives and the concept of limits. If I make another video, the first topic we will cover will be limits, as it's the foundation of both of them. And hopefully this served as a fairly instructional video, and if you guys have any recommendations for other videos, I would appreciate that. If this goes well, I may consider making a Patreon, and I would hope that people that enjoy my content would subscribe, and if you could, donate. Thank you for your time. Also, where is calculus used? That's a silly question. It's used everywhere. We'll see that soon. All right, take care.